Hello, we're glad you've joined us for this live webinar, Freeze Drying Solutions for Your Lab. I am Michelle Ashton of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is brought to you by LabRoots and sponsored by Labconco. For more information on our sponsor, please visit www.labconco.com. Now let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the slide window, click on the arrows at the top right-hand corner of the slide window. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab at the top right of the presentation window and follow the process to obtain your credits. I'd like to now introduce our presenters, Megan Zimmerman, Product Manager, and Jenny Sprung, Senior Application Specialist at Labconco Corporation. To learn more about our speakers, please visit the Speaker tab at the top of the presentation window. Our speakers will now begin their presentations.
Thank you, Michelle, and thank you to everyone for joining us. Today we'll be talking about freeze-drying solutions for your lab. We'll start by discussing a general overview of the freeze-drying process, followed by how to select a freeze dryer to meet your needs. Then I'll pass things off to Jenny, and she'll talk about how to develop a protocol, freeze-drying challenging samples, and troubleshooting. First, we'll start by discussing some common terms you'll hear when talking about freeze-drying. Freeze-drying is the process of removing moisture from a frozen product using a vacuum. But another term you might hear is lyophilization, which is another word for freeze-drying that is derived from the Greek word solvent-loving. Lyophilized samples are easily rehydrated, making it a great process for sample preparation because you can easily resuspend your samples. Sublimation is also a word you'll hear when talking about freeze-drying. This is the process in freeze-drying in which solvents pass directly from the solid phase to the gas phase, giving freeze-dried samples such great preservation properties because you are bypassing the liquid phase. The rate at which sublimation occurs is dependent on temperature and pressure. This graph shows what's happening to your sample when you freeze-dry. For sublimation to occur, you need to have a cold enough temperature and a deep enough vacuum for your sample to go from a solid to a gas. If either of these things doesn't occur, the sample will actually evaporate and not get the preservation properties that you would get with sublimation. This makes pressure and temperature critical components of freeze-drying. When freeze-drying, it's important to cool the material below its triple point, which is shown on the graph. The triple point is the highest temperature at which the solid and liquid phases of the material can coexist. Being below this point ensures that sublimation rather than evaporation will occur. Next, we'll talk about the requirements you need for a successful freeze-drying process. The first requirement of freeze-drying is that you have a pre-frozen sample before you start your run. When you put your frozen sample on the freeze dryer, it will be subject to melting until the appropriate vacuum level is established. You may see this melting occur with older vacuum pumps or pumps that aren't working well, because it will take longer for that vacuum to pull down. Having a vacuum pump in good working order is extremely important for the success of your freeze-dried samples. The second requirement of freeze-drying is that you have a collector that is 15 to 20 degrees colder than the sample's freezing point in order to trap the vapor coming off your sample. By nature, water molecules from your sample will want to move to the coldest spot in the system, which is the collector coil. This natural migration of water molecules is called cryopumping. The third requirement for freeze-drying is having a deep vacuum, with a minimum requirement of 0.002 millibar. This is necessary because the vacuum pump establishes negative pressure, forcing free-flowing water molecules that have left the sample by sublimation to evacuate from the environment around the sample and travel to the collector coil. The last requirement for freeze drying is having energy in the form of heat. While not obvious to a lot of people, the lyophilization process is essentially a heat transfer process. For example, with flask freeze drying, the flask is hanging at room temperature and the ambient heat from the room is what's driving the process. In general, the more heat you're able to apply to your samples, the faster your run will go. However, not all samples can take the same amount of heat input. If you add too much heat to certain samples, you could cause your samples to melt. These images are showing the difference between uncontrolled heat and controlled heat. With uncontrolled heat, the flask is receiving ambient heat from the air in the room, making it hard to control. For samples in the pharmaceutical industry or production samples, people will typically use a tray dryer so they can apply controlled heat to their samples. When freeze drying, there are 3 stages that occur. First is the pre-freezing stage, where you start with a completely frozen sample. This is followed by primary and then secondary drying. For many laboratories, there isn't much difference between these 2 stages, but for pharmaceuticals or more sophisticated freeze drying runs, there's a distinct difference. This graph shows the data of a freeze drying run throughout the 3 stages of the process. The blue line represents the shelf temperature, while the green line represents the temperature of the sample. The graph begins by showing the freezing of the product. When the sample temperature matches the shelf temperature, freezing of the sample has occurred. This stage is then held for a while to ensure the entire sample is completely frozen. After the hold, you see the shelf temperature start to climb in primary drying. However, the sample temperature no longer correlates to the rise in the shelf temperature. This is because the sample is undergoing evaporative cooling, which suppresses the temperature. This is also what allows you to add heat to your sample during primary drying. With the addition of this heat, you are increasing the rate of sublimation and shortening your run time. Primary drying continues until your shelf temperature and sample temperature meet. For most laboratories that are planning to resuspend their samples, this is the point when they would typically end the run, with their samples containing about 7 to 8% moisture. However, for end users who are preparing their samples for long-term preservation, they will continue their run into secondary drying. Secondary drying is where water molecules that are bound to a sample are released. With the additional heat in this last stage, you are able to drive those bound water molecules out of your sample, leaving behind about 2% moisture. For more sophisticated freeze drying, you can send your samples off to companies where they'll watch the freeze drying process under a microscope. They can then tell you your sample's triple point and what amount of heat input would be good for your run. In general, most labs will just guesstimate the heat input, fine-tuning their process to develop an optimized lyophilization run. Now let's talk through each of the 3 stages of freeze drying in a little more detail. In the pre-freezing stage, if you're freezing your sample in a flask, you'll want to make sure you're freezing your sample in a way that gives you the greatest chance for efficiency during the run. The first example on the left shows stub freezing, which is keeping your sample on a flat surface and is not a good way to freeze your sample. The example in the middle is called slant freezing, where you keep your sample at an angle while it freezes. By doing this, you're increasing the surface area of the sample, which helps reduce your overall run time. The example on the right, shell freezing, is the most optimal way to freeze your sample, especially when you're working with large volumes. What shell freezing does is roll the sample while it's freezing in a very cold solution to create a thin coating over the entire surface of the flask. This gives you the largest surface area and reduces the amount of sample the water molecules have to move through during freeze drying. Once your sample is frozen and you start your freeze dryer, you'll begin primary drying. As you can see in the picture, there is so much evaporative cooling happening during this step that you will get frost buildup on the outside of your flask. This is a good indication that your freeze drying process is going well. If you see the frost start to melt as well as your sample, this is indicating that there is a problem with your run. At this point, you are no longer freeze drying and your sample is undergoing evaporation. When we are able to control heat input in primary drying, the temperature your sample is at plays an important role in your run. While some samples can take a lot of heat, other samples don't do well with heat input. The example shown is from a paper where they studied the effects of freeze drying the same sample at different temperatures. The example on the bottom left shows the result of a collapsed cake. A cake is what you call the remaining product after you freeze dry a sample. With this run, the sample melted and underwent evaporation instead of sublimation when the shelf temperature was set at -10 degrees Celsius and the product was at -15 degrees Celsius. The example on the bottom right shows a result of a partially collapsed cake. With this run, they adjusted their shelf temperature to -15 degrees Celsius. With the last example on the top right, they again adjusted their shelf temperature to -20 degrees Celsius with a product temperature of -25 degrees Celsius and had a finished product with an excellent cake. So you can see that even though none of these runs had a difference of more than 5 degrees Celsius from one to the other, there was still a very big difference in how the final product turned out. This is why you'll have to fine-tune your process to develop a protocol that will give you the best cake unless you plan to send your samples off to be tested. After primary drying is complete, you move into secondary drying, where you are releasing the remaining water molecules that are bound to the sample. In order to complete secondary drying, you need a freeze dryer that has shelves so you can supply additional heat to your samples and get the moisture content down to about 2%. For long-term storage of your samples, you will want to complete secondary drying, and you'll also want to stopper or seal your samples under a vacuum. By stoppering your samples under vacuum, you avoid exposing your samples to the moisture in the air when you open the door. Another way to achieve long-term storage is to flame seal your samples and ampules before the vacuum is released. Next, I'm going to talk about selecting a freeze dryer that meets the needs of your lab. The first thing you'll want to think about is who all will be using the freeze dryer. Is this purchased just for your lab, or will multiple groups be using the freeze dryer? Find out what kind of samples each person plans to use for the unit. Looking at the types of solvents and acids that make up their samples. Also determine who will be responsible for maintenance, such as cleaning the coils and performing oil changes on the vacuum pump. This will help to keep your freeze dryer and vacuum pump in optimal working condition. Choosing the right materials for your freeze dryer is important when making your selection. Many solvents used in samples can attack plastic and rubber components, which can cause vacuum leaks over time. Because of this, it's important that you know what kind of solvents and acids everyone will be using, because you'll want to make sure the samples will be compatible with the materials of the freeze dryer. Other than knowing what kinds of solvents you'll be using, you will also want to determine the collector temperature you need, keeping in mind that the temperature should be 15 to 20 degrees colder than the freezing point of your samples. Freeze dryers typically come in collector temperatures of -50, -84, and -105 degrees Celsius. You also need to determine the collector size of your freeze dryer. Freeze dryers are described by their ice holding capacity. So if you're looking at a 4.5 liter freeze dryer, that means it can hold 4.5 liters of ice before needing to be defrosted. This does not mean that you can put 4.5 liters of sample on the freeze dryer, but instead you'd be able to put about half of that volume on there to accommodate all the vapors that will come off your samples when you start your run. The next thing you need to determine is the type of vacuum pump you need. Freeze drying requires that the pump be able to reach 100 microns with a displacement of at least 98 liters per minute. When selecting your freeze dryer, you'll also need to consider the accessories you'll need. Besides offering flasks and serum bottles, we also offer items like tube racks and microplate holders. With microplates, since you're working with such small volume of samples, it's very easy for that sample to start melting quickly. With our microplate holder, you can place your microplate on the holder while you're freezing your sample and keep it on there during your run to help keep the sample frozen while your vacuum is cooling down. Another thing to consider when selecting a freeze dryer is the coil design. With our internal coil design, we are able to provide the coldest possible temperatures and are superior in capturing the solvents coming off of samples compared to an external coil design that is on the outside of the collector. Additional things to keep in mind when selecting a freeze dryer. What kind of controls does your freeze dryer need? What do you need to get the appropriate data and results from your run? Do you need your freeze dryer to meet CGMP standards? Do you need a freeze dryer with shelves to pre-freeze your samples? When you're controlling your freeze dryer, what kind of software and programming do you need? How are you accessing your data? With our LyoWorks operating system, you'll be able to download your data to a USB flash drive or use an Ethernet connection to send your run data straight to your computer through a one-way connection. We also offer remote notification with the ability to configure the types of alerts that are sent to your email. Since freeze-drying runs can sometimes last for days, leaving you wondering how your samples are doing while you're away from the lab, you can have alerts sent to your phone showing you the parameters of the run, giving you peace of mind. A vacuum control valve is another important feature to have in your freeze dryer. By being able to set the vacuum level, you're able to speed your runtime of certain solvents. Many people think if they pull the deepest vacuum, it will speed their run, but that isn't the case. Having your sample set at about 0.2 millibar is actually the most efficient vacuum setting. Endpoint detection is another feature to consider if you're freeze drying in Flask. Oftentimes, it can be difficult to tell if your sample is done, which leads people to sometimes take their samples off too soon, only to realize the run wasn't complete and causing them to start the run over. Or they are leaving their samples on for much longer than they really need just to ensure their sample is finished, wasting time and energy the freeze dryer is using. Our endpoint detection helps you avoid both of these outcomes by alerting you to when your samples have achieved the level of dryness that you've set. Now I'm going to pass things over to Jenny, where she'll discuss developing a protocol.
Great, thank you, Megan. We're going to be discussing how to work with your freeze dryer to make the most out of it. Now that you know how to choose your freeze dryer and what drying chambers you want, we can discuss how to move forward with developing your protocol. In a typical freeze-dry cycle, you would want to pre-freeze your sample, whether it be on your shelf or in a flask. So that's the first determining factor. If you're freeze-drying on controlled heated shelves and controlled refrigerated shelves, then you would set up your main drying system. If you're freeze-drying in flask, you would attach your frozen flask to a port and let the freeze dryer do its job. To optimize your program and your process, you never want to overfill your containers. What will happen is you could potentially break your flask, or it will take a very long time for your freeze-dry process to go. Thin surface area is better on your trays as well as in your flask. As Megan discussed, pre-freezing on a slant or in a shell are the best ways to do it. You want to consider your pump requirements. If you don't want to do a lot of maintenance, a dry or scroll pump would be your best option. You do need to make sure that you have a specific minimum requirement for your pump in order for it to do freeze-dry work. Never oversize or undersize your vacuum pump. The pre-freeze step is the most important step in freeze drying. You don't want to end up with a sample that will melt immediately on your freeze dryer because you did not freeze dry correctly or long enough. The greater surface area, the better when freeze drying your samples. There are two ways to pre-freeze a sample. You can do this quickly or you can do it slowly. The rate of your pre-freezing will affect the ice crystal size of your sample. Faster pre-freezing will create smaller ice crystals, where a controlled cooling will create larger ice crystals that are typically quicker to freeze dry. Once your sample is completely frozen, you will move on to primary drying. You want to add a little bit of heat transfer during this step, but not melt the sample. So this is a very important step in your freeze-dry process. Make sure during the run that your samples are not melting and you're not seeing any bubbling in your flask or on your tray dryer. If you do start seeing melt back, you can refreeze your sample or lower the shelf temperature if you're running on shelf. You also need to look at your room conditions. A warm room could also create melt back. You want your room about ambient temperature or 22 degrees Celsius for the best conditions. If the room is too small, it could get too hot based on your vacuum pump running as well as your collector running. So a medium to large size room will be better. You don't want the freeze dryer in direct sun. If it's under a window, the heat caused from the sun could also cause melt back to your samples. And if your freezer is located in another room or another building, make sure you are insulating those samples on the walk to get to the freeze dryer. Some samples could require additives. If the samples are freeze sensitive, you might want to add a lyoprotectant. If you are worried about losing your active ingredient, you may want to use a keeper solvent. This will all be dependent on your specific sample and needs to be thought about prior to the freeze-dry process. CGMP is another thing to keep in mind when you're purchasing a freeze dryer. According to CGMP regulations, our freeze dryers can be used and you can modify them to your CGMP requirements. Most standard equipment have flexibility for you to modify this in your lab based on your needs. What we can provide for you are materials of construction, the test reports that are done on your specific freeze dryer that we've done in-house. We can offer manuals, videos, and documents. We also offer IQ/OQ for you to check those processes on your own, and PQ can be done by an outside consulting group. There are many challenging samples that are difficult to be freeze-dried. One would be tert butyl alcohol. The end product is not going to be a powder. It will come out more of a gummy mass at the bottom of the flask. This is very normal, and other samples may turn out like this as well. Another challenge would be to freeze-dry alcohols. Methanol and ethanol have very low freezing points, which make it difficult to keep frozen, as well as finding a collector temperature that will work for your needs. These alcohols must be dilute, about 10% or less, in order for them to freeze-dry correctly. DMSO as well as DMF tend to attack rubber and plastic components, so these components may be replaced over time. Sugars and salts tend to lower the eutectic temperature of your sample, which may require a cascade or -84-degree model. And a HEPA filter would be useful in line to protect your vacuum pump from any particulates coming through. Soil samples also tend to migrate towards the pump once they become dry, so a HEPA filter is recommended for soil samples. If you're running whole samples, it's best to homogenize those samples, or at a minimum, poke holes in those samples to allow the vapors to leave. When you're running a freeze dryer, there's a couple things that could happen. The first one is that the samples won't stay frozen during the process. So you do need to look to make sure that your freeze dryer is the correct model and that you do have the temperature differential between the frozen sample and your collector temperature. If there are small samples or in plastic vials, that could also cause some melt back during the run, or if there's too high of an alcohol content in them, they may not pre-freeze correctly. Also, you want to watch your vacuum pressure to make sure that your vacuum is at a good level. If samples are being pulled out by the vacuum, you can use filter paper or parafilm as long as there's holes poked into the sample to allow for the vapors to leave. And if samples are taking too long to lyophilize, your shelf temperature may be too cold, your sample might be too thick, or there may not be enough headspace in the vials. Once you're running, you do want to monitor your vacuum level. If you don't have a low enough vacuum level, there could be a couple reasons. You may have cracks in your gaskets. There might be dirt or debris on your gaskets, or you might even need to just do an oil change on your oil pump. So these are all things that you want to take a look at before running a sample to make sure that you're going to get optimal processes. If your final product looks different each time, this might be normal, depending again on your sample. Different samples will freeze dry differently, and it could be the outcome of your room temperature, the purity of your solvents, as well as the percent of active ingredient from sample to sample. If you are worried about a cake versus powder, what you want to look at is what solvents are being used, what the temperature is prior to putting that solvent on the freeze dryer, and also pH shifts during the process. If you are using a hybrid pump or a rotary vane pump, oil changes are very important and must be done. A scroll pump is an oil-free pump, however, that will also require some maintenance. To do an oil change, you do just want to follow the manufacturer's recommendation on how to do an oil change and make sure you're using the correct oil for your pump. A hybrid pump will take a synthetic oil. If you don't do oil changes, this could be the outcome of your pump. And at this point, unfortunately, the pump cannot be repaired because it is beyond that point. If possible, you want to open your gas ballast after each run. By opening your gas ballast to number 2 and running the system under vacuum for about 15 minutes, you're able to purge any contaminants out of the oil of the pump and help the pump run longer. That concludes this webinar. If you have any questions, we would be happy to answer them.
Thank you, Megan and Jenny, for your informative presentations. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many questions as we have time for. Let's get started. Our first question is, will my current vacuum pump work with a Labconco freeze dryer?
That's a really great question. So when we test our products, we obviously test them with the Edwards and Vacuum brand vacuum pumps that we offer. So we can always guarantee that those products will work with our freeze dryers. But what we tell our customers with other freeze dryers, or other vacuum pumps, I should say, is that the minimum requirement to use our benchtop freeze dryers is a displacement of 98 liters per minute. Now, with our larger units of consoles with a stop ring or a bulk tray dryer on top, that number goes up to 163 liters per minute. So really, it's just checking with the technical specifications of the vacuum pump you currently have.
Thank you. All right, your next question is, how can I seal under vacuum without buying a stop ring tray dryer?
With our mini stoppering tray dryer, you are able to stopper off of ports. You can also stopper under a gas, so a seal torch flame, which works on ampules. Those are the two best ways to do it without the stoppering tray dryer. Keep in mind that the stoppering tray dryer will allow you to pre-freeze your samples as well as do heating and then stoppering all automatically. The other two options will be more manual, and in the mini stoppering chamber, as well as if you do the flame torching, you will have to pre-freeze those samples prior to putting them on the freeze dryer. But they're two great alternatives to spending the extra money on a stoppering tray dryer.
Great, thank you. Your next question is, how does end zone endpoint detection work?
So with our end zone endpoint detection, like we talked about in the webinar, the whole idea behind it is to alert you when your freeze-dried samples in a flask are dry. And so the way that it's doing that is the end zone kit comes with two vacuum sensors. One goes into an empty port on your manifold. The other goes into a port on the top of your sample. And when the endpoint has been reached, what it's doing is comparing the vacuum level of that empty valve to the vacuum level of your sample. So when those are even, that's when your system knows that your sample is dry to the level that you've specified.
I want to once again thank Megan and Jenny. Before we go, I'd also like to thank the audience for joining us today and for their questions. Questions we did not have time for today or those submitted during the on-demand period will be addressed by the speakers via the contact information you provided at the time of registration. We would like to thank LabRoots and our sponsor Labconco for underwriting today's educational webcast. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.